Hey y'all, in this lesson, we're going to be using the complement of sets to learn about probability when you see the word not in the problem. So if we review complements of sets for just a second, what is the complement? If you remember from previous lessons, the complement of a set, if we have set A, for example, the complement of set A is everything in the universal set that's not in A. I have an example down here. If we consider the universal set a deck of cards, a standard deck of cards, and we call subset A to be red cards, then first we want to talk about how many cards are in the universal set. In a standard deck of cards, there are 52 cards. And then how many red cards are there? Half of them are red, so 26. And then it says find a complement. So the complement of A would be every card that's not red. Any of the cards that are not red are black cards. And there are 26 of those. And then if we total up A and A complement, the complement of A, so how many total cards are in A? And the complement of A, there's 52 total cards, which is how many cards are in the universal set. So we're going to be using this idea to help us figure out probability when they say not. So not red or not spade or not anything like that, not four. So let's go over some basics of probability before we get into probability with not. A probability of any event is always between 0 and 1, or 0 and 100%, where 0 indicates that the event never occurred and 1 indicates that it certainly occurs. So when we had the sum of the dice, and if I said find the probability of having a sum of 1, that would be 0 because there's no chance of that happening. The probability of all of the events in an experiment will add up to 1. So you kind of think of a pie chart in this situation where each wedge of the pie is a certain percentage or probability, and all of those pieces add up to one whole. So same thing here, if we have several different events or subsets of the universal set, for example, if I find the probability of each, all of those probabilities will add up to 1. If they don't, you've done something wrong. So I have just a simple example here, a probability distribution table. So it's how the probability is distributed among each event. So each event is one side of a die, and the probability of rolling a 1 on a 6-sided die is 1/6. And this is a fair die, so each side is going to have equal likelihood of being rolled. Even if you use empirical probability where maybe these are different values, may not be an even 1/6, they will still add up to 1. This adds up to 6/6, which is 1. So that's just kind of how to show you that. So let's look at the complement and the word not. Fill in the probability distribution table for a standard deck of cards. The probability of drawing a red card, we found that there were 26 red cards out of 52. I'm just going to leave it non-simplified for now because it's going to work out in the end. And then not drawing a red card, that means you're drawing a black card. And we know that there's 26 out of 52 for a total of 52 out of 52, which is 1. And this leads us to our rule down here. Not drawing a red card and drawing a red card would be considered two sets that are complements. And in general, when you find the probability of a set A and the probability of its complement, those two will add up to 1. Or we can kind of manipulate that equation, subtract this over, and have this instead. They're the same. they're just, one looks a little different. So it depends on the situation, which one you would want to use. When a single card is drawn from a standard deck of cards, find the probability that the card will not be a king. So we know that we're talking about a total of 52 cards, and 4 of those are kings. But we want to know the cards that are not kings. So I can use this idea here of subtracting. If I know that what I'm looking for is not king, then I can do 1 minus kings to figure out all the other stuff. So I can do 1 minus the probability of kings, and that's going to give us 1 minus 4 over 52. I can reduce that 4 over 52 ahead of time if you want, but we can reduce in the last step instead. So I'm finding the probability of complement of kings, not king. And so this looks a little different than this equation. I basically, I've subtracted this over instead, but it's going to give us the same solution. But essentially what we're doing is we're taking the fact that we know that the probability of a king and the probability of not king is going to add up to 1. So we can figure out that not king by doing 1 minus. So we're kind of finding that missing piece. And then we can subtract these, get a common denominator. You can type this in your calculator if you prefer. And we get 48 over 52, which will reduce by 4 to get 12 over 13. And this would have been, if we had reduced this, we would have gotten 1 over 13. So you can see that 1 over 13 and 12 over 13 add up to 13 over 13, which is 1. So that's how we know we've done it correctly. Last example here, the probability of an event, doesn't matter what the event is a third. What is the probability that event E will not occur? So go ahead and pause it, try it, and come back. Hopefully what you did is the probability of the complement of E is 1 minus the probability of E. So we sub in the probability of E, common denominator, and we get 2/3. And you can check it because these two numbers should add up to 1, and they do. So that's it. That's all I have for this lesson. I hope you enjoyed it. If you have any questions, please let me know, and I'd be happy to help. See you in the next one.